So let us continue our yesterday's discussion that was on Hall effect. Yeah. So I hope I'm audible because I need to complete this Hall effect. So I'm going to continue. I'm going to start straight away. And please type your attendance again in the chat box. So like usual, type it your roll number in full, complete roll number. Okay, starting with, yeah, you all know it. Now, this is our problem. We have a semiconductor. Semiconductor dimension is having a length L, thickness T, and width W. So it is a semiconductor having this dimension. And now if you look at this semiconductor, we consider here, what will be the cross-sectional area? See, what we mean by cross-sectional area. Now, suppose I have a semiconductor like this. I have a semiconductor or a metallic conductor, also whatever. If you have a semiconductor, and even if it's a long semiconductor, if you cut that semiconductor perpendicular to the length, so the area within this, so this area within this shaded region is called the cross-sectional area. This is what we mean by the cross-sectional area. And L is the length here. So if you have a current I passing through this semiconductor, suppose this is the current flowing through this, and if the cross-sectional area is A here, then the current density J is given as current per unit cross-sectional area. This is how we define a current density, current per unit area. Now, instead of this cylindrical, suppose I have a rectangular semiconductor, something like this. Rectangular semiconductor having thickness T, width W, and length L, like this. So the cross-sectional area here in this case will be the area as denoted by this shaded region. So how do we determine this area? This cross-sectional area A will be simply width into thickness. And if I is the current passing through this semiconductor along the length L, the current density J will be current upon cross-sectional area, that is current upon W, width into thickness. Okay, this is how we we write the cross-sectional area and the current density. Now, like we discussed, in this particular problem, we define our coordinate system like this. So this is our coordinate system. This along this direction is x-axis, and y direction is towards the behind the screen, and z direction is upward of the screen. And as you see here, magnetic field is along the upward direction. And by looking at this, there is a positive terminal, negative terminal of the battery here. So this is how we denote a DC battery. A DC battery, the broader side is the positive terminal and the smaller side is the negative terminal. So that means you're having a positive voltage applied here, you're having a negative voltage applied here. And according to this, if you apply a V volt here, and the length L here, then you will have a resultant electric field within this along this direction. So this is how the electric field will be. So if you look at the electric field direction here, this side being positive, this side being negative, according to this applied voltage, the electric field within this semiconductor will have the same direction as the x-axis. So that means your electric field is along the x-axis. All right, Ex. Likewise, the magnetic field is pointing along the z-axis. So you have a magnetic field component only along the z-axis. So Bz. No other magnetic field component like Bx, Bx, By, they are all zero because you have a magnetic field along the x-axis, sorry, z-axis only. And likewise, the electric field applied according to this applied voltage is along the x-axis. Applied electric field is along the x-axis. And now, under the action of this electric field, suppose you have a certain charge carriers like free electrons. Free electrons. Suppose this is semiconductor is n-type. Suppose our semiconductor is n-type. That means you have plenty of free electrons within this semiconductor. So under the action of this electric field or the applied voltage, these electrons will start moving, and the motion of electrons will result in electrical current or net transfer of charge. Because electrons, instead of random direction, let me put it like this. Suppose you do not have any electric field. Suppose you do not have any electric field within this semiconductor. Let's say you have, this is a n-type semiconductor. N-type semiconductor. So in this n-type semiconductor, you have large quantity of majority charge carriers, free electrons. Without electric field, the only energy provided to these free electrons will be your random thermal energy 3/2 kT will be the average kinetic energy. So this average kinetic energy is a random thermal energy. It does not have any specific direction. So some of them will move in this direction, some of them will move in this direction, some of them will move downwards, some of them will move upwards, some of them will move like this, some of them will move like this. So random motion, as a result of this thermal energy 3/2 kT, it cannot contribute to any net transfer of charge. So as it cannot contribute to any net transfer of charge, that means you cannot have any current according to this random thermal energy, right? So therefore, you cannot have any current in a semiconductor or a conductor also. A current will occur only you connect this to external battery source like positive, negative, positive, negative. So if you connect to external battery source like this side will become positive and this side will become negative, and then whatever we are going to discuss, it will happen, right? Like the one I shown here. So under the action of this external applied voltage or the electric field here, these electrons will start moving with a velocity Vx along the x-axis. They will start moving along this with Vx, moving along this with Vx. So if they start moving along, someone is texting me. If they start moving along this direction, and under the action of this magnetic field, we know that there is a Lorentz force. So the Lorentz force acting on this moving charge will be the charge Q into Vx cross Bz, right? So because of the electronic charge, Q is taken as mod of Q, minus of mod of Q. So this is how we are going to do, right? So as I was saying, yeah, the electric field, of course, I think I discussed this. The electric field is simply given by this. Ex is equal to V upon L, because here, as you see, V is the voltage acting on the different end. The potential at this point and the potential at this point will have a potential difference of V, and L is the length. So the electric field here will be V upon L here. You are applying a V voltage here. On the left side, you have a supplied positive terminal, and on the right side, you have negative supply negative terminal. and the applied voltage is V, and your electric field will be voltage upon separation of the 2 points where you apply a voltage potential difference. Okay, V upon L will be your electric field here. Now, so this is V upon L, the electric field. I hope you are all convinced. This is from the basic definition of electric field and potential in class 9 and 10. I think it was in 10. Now, for a semiconductor of N type, you can write the charge as mass of a certain charge, that is mod of Q, the electronic charge, 1.9 10 to the power minus 19 coulomb is the charge here. So electron being negative, you put negative. And the Lorentz force here will be along the y direction, as I explained before. See, this is along your velocity of motion is along x-axis, along the negative x-axis, and you have a magnetic field along this direction. Now, if you take a cross product, in your Lorentz force, the v vector is the first vector. So considering v as the first vector here, you have to take the rotation along this. Okay, v as the first vector, you have to take rotation along this. If you take a rotation along this, and like I said, use your right hand thumb rule, and if you use all your index fingers and all as pointing the direction of rotation, your thumb as a direction of the resultant field. So your resultant vector, that is Vx cross Bz, the product of these two vectors will result in a new vector along the direction of y. So this is your coordinate axis, x, y, z. If you remember, this is how we define our coordinate axis. So that means your resultant force will be along y. All right. But since the charge carriers in n-type is of negative charge, that is electrons, q is replaced by minus q, and therefore the resultant force will be not along the y-axis, it will be reverse of the y-axis, that is towards the front side of the screen. Now, coming back to this, so you have this Vx here, you have a Bz here, and you have a resultant force towards the screen. That is, the resultant force acting on the moving charge is towards the screen. That is, I mean, facing you. Then that means these electrons, under the action of this Lorentz force, they will start deviating, and some of the electrons will get deposited on the front surface. Electrons will get deposited on the front surface as it moves. Under the action of the Lorentz force, it will be deposited on the front surface. And under the action of this Lorentz force, when you set the electron in motion, more and more electronic charge will accumulate. Now, when more charges accumulate here, like you see here, this is, let me redraw it like this. This is your width, this is thickness. Now, we assume that under the action of this Lorentz force, more electronic charges, negative charges are accumulating here. So if more negative charges accumulating on the front surface, on the back surface, that is on the back surface here, there will be a deficiency. On the back surface here, there will be deficiency of electrons. So that means you will have electric field like this along the y-axis, electric field along the y-axis. All right. So this electric field is what we define as Hall field. Okay. And the potential developed across this semiconductor is known as Hall voltage. Okay, can you understand the point I'm trying to make here? Say, this is the length of the semiconductor. This is the length of the semiconductor, and you are already applying external voltage here, positive, negative. This external voltage is along the x-axis. If you remember, external voltage is along the x-axis. In addition to the applied external voltage, once you have this electron, that is the charge carriers deposited on the front surface of this semiconductor here on this surface, once the electrons are deposited on this surface, it will result in a formation of electric field or potential difference across the semiconductor, that is from the back to front, from the back to front. So this transverse electric field or transverse potential that is developed across the semiconductor under the action of the Lorentz force is known as your Hall voltage. This was the applied voltage. So the applied voltage is along X, but the Hall voltage is along the Y axis. Okay, so please try to picture that. Now, once more and more charges are accumulated, then this surface will accumulate more charges. That means the Hall voltage here will be stronger, and the electric field, transverse electric field, will be getting stronger and stronger. And eventually, the electrons deposited on the front surface will have sufficient energy to repel any incoming electrons. So more electronic charges accumulating on the front surface means more and more negative charges will be there on the front surface to repel any further accumulation of the electronic charge. It will repel any further accumulation of electronic charge. And then after that, electrons, instead of deviating and coming to the front surface, it will move in this direction. Okay, so initially electrons get deposited on the front surface. Once enough charge is accumulated, an equilibrium will be attained. An equilibrium in the sense the Lorentz force that is deviating or forcing the electrons to get deposited on the front surface, if it is equal to the force due to this electric field Ey, the force due to this electric field Ey, then the Lorentz force can no longer make these moving electrons deposited on the front surface. It will be cancelled out by the Hall voltage or the Hall field. Okay, so an equilibrium is this condition. So this is your the force due to the Hall electric field. So you have this electric field Ey, okay, and this side being negative, the front side being negative, Ey. So this is your Lorentz force. So if you have a charge Q here, if Q is moving, the force due to this Ey, the whole field will be Q into Ey. The magnitude is simply this. So the magnitude of this force, once it equals the Lorentz force, then equilibrium will be attained. No more accumulation or no more deviation of charge, right? So that is the equilibrium state. So under such equilibrium state, you already have a whole, you have already set up a Hall field of Ui, and correspondingly Hall voltage of, what will be your Hall voltage here? W is the width here, and Ey is the electric field, Hall field here. W into Ey will be your Hall voltage. Okay, W into Ey will be your Hall voltage, or Ey will be voltage, Hall voltage upon W. Okay, let us denote this Hall voltage as V subscript H, Hall voltage. Hall voltage will be W into Ey. Now, so here you can see that just by taking the magnitude of force means the negative charge will cancel, the negative charge will be gone, and Q will cancel out. And we know that this Vx is along X and Bz is along B is along Z axis, so there is a 90-degree between them. So if you take a cross product here, this is simply magnitude of Vx, magnitude of Bz, and sine of the angle of between them, sine 90-degree, and unit vector. So by taking the magnitude, all the unit vector is gone. So this is simply Vx Bz sine 90 is 1. Okay. So if you simplify that, if you do the cross product, this is what you will get. Ey is equal to Vx into Bz. All right. Now the current flowing in the n-type semiconductor, the current density, like we discussed before, I think I have discussed this relation. If you can just revise it also. So the current density under the action of that externally applied field will be Jx is equal to Q, the charge into concentration of charge, into velocity of motion of the charge, because the charge, like the electrons, they are moving along the x-axis, you remember. And the current density, as I already discussed, it is the current along the x-axis upon cross-sectional area. Now from this you can write your current as jx into a. Okay, your jx is q into n into vx. Jx is q into n into vx into a. So this is your current. So q into n into vx into a. A is, as we discussed, w into t, and q is the electronic charge, the electron charge being negative charge minus of this. And from this you can write your vx as the velocity as this, velocity of motion of the electrons as this. Okay, now from this uy equal to vx into bz, we already know it. Uy is equal to vx into bz. You just put the value of vx, then you will get this uy as this, right? Now whole voltage, yeah, as I said, so this is, like I said, I define this is w is the width, w is the width. So you have a electric field, electrons being deposited on the front surface. You have electric field like this. So this is your along y-axis. So the whole voltage is w into electric field. Here from the figure you can see that w into uy, and your uy, we already determined uy here, so you can just put the value of uy. This is your relation number 2, gives you your whole voltage. Now whole coefficient, whole coefficient is defined as a ratio of electric field, whole field, upon the product of current density and the applied magnetic field. Okay, so this is a ratio of the resultant. Uy is the resultant of the action of this current and the magnetic field. See, you are applying in a semiconductor, let me rephrase you. You are applying voltage here. So under the action of this voltage, there will be a current Ix. So your current Ix is simply Jx is equal to Ix upon cross-sectional area. So Ix is what the current you are passing through the semiconductor. The current you are passing through the semiconductor. Bz is the applied field. So you are passing a current of Ix and you are applying Bz in a semiconductor. So that results in what? That results in a whole field of Uy. So Uy is a result of the current passing to the semiconductor and the applied magnetic field. So the ratio, that is Uy, the result, upon the causes, that is the current into magnetic field. This ratio is known as Hall coefficient. Okay, so Ey, as we know it, it is Vh upon W. Jx is Ix upon A is W into T. And if you just put all these values, Vh value you put, you substitute all this thing, and then subsequently you get the whole coefficient as minus of 1 upon mod of charge, magnitude of the charge into number density of the charge, n. All right. Now, if a semiconductor is p-type, the only difference here will be q is replaced with positive plus of mod of q. And yeah, what time is it? Yeah, I have time. Now, if you do this here, now let us picture. So this is your semiconductor. This is your semiconductor. You are applying a potential just like the previous case. So this side is positive, this side is negative, and you have applied the electric field like this, Ex, right? Applied the electric field. And if you have a p-type semiconductor, you have holes. You have holes, right? Holes, they are behaving like positive charge carriers. Okay, so these holes, instead of moving in this direction, they will move along this direction. So you apply a magnetic field along the z, bz. Now the velocity of motion is vx. Now if you consider your Lorentz force here, that is q into vx cross bz, q into vx cross bz. If you take the vector direction like this, vx and bz. Now the rotation, the vx is the first vector, so the rotation has to come from the first vector. So the rotation is like this. Okay, if the rotation is like this, use your right hand thumb rule to indicate the direction of this cross product vector. So your other fingers will represent your direction of rotation here. Your thumb will represent direction of the resultant vector. All right. So if you do that, you will find that the resultant force is towards the screen or towards you, away from the towards you. The resultant force will be pointing towards you. If you look at the screen, the resultant force will be pointing towards you, right? So this is along also y. So because of this action of this force, you also know that q is a positive charge, mean there is no reversal direction. So here in this case, as the charged particles move, they will get deposited on the front surface. So on the front surface, you will have large quantity of holes. And on the back surface, there will be deficiency of holes, because if you collect the holes on the front surface, there will be deficiency of holes. And then the resultant electric field, the resultant hole field, EY, will be along this direction. Now see the difference here. In the earlier case here, in the n-type semiconductor, under the action of this Lorentz force, electrons are deposited on the front surface, and you have electric field along this direction. This was your electric field along this direction. That is, electric field has to have a direction from positive to negative, right? So electric field, the result electric field is along this direction. Electrons are deposited on the front surface. Now, if you consider a p-type semiconductor, under the action of this Lorentz force, holes will be deposited on the front surface, and there will be deficiency of holes on the back side, and then the electric field is along this. So the whole field will be of reverse polarity here, in comparison with the n-type. And instead of electrons deposited on the front surface, you have holes deposited on the front surface. All right, holes deposited on the front surface. So that is the difference here. Now, if you continue the usual calculation in equilibrium, this force will match this force. So all these things are usual. I think you can continue all these things because they are same thing. And eventually, you will get your whole coefficient as this. So the same calculation, if you follow, the whole coefficient will be this. That is plus of 1 upon mod of q into p. P is number of holes per unit volume, number density of this, right? Now, like I discussed before. So magnitude of charge means simply 1.9 × 10⁻⁹ coulomb. Yeah, that is your Hall coefficient. So here in this case, Hall coefficient is positive. In the case of n-type, Hall coefficient was negative. Now, what is the why do we study this Hall coefficient? The advantage or the application of Hall coefficient is that once you determine the Hall coefficient experimentally, you can determine the type of semiconductor, whether it's a p-type or n-type. How do we determine this Hall coefficient experimentally? You know that Bz is the applied field. So if you have a semiconductor sample here, using electromagnets, you can control the applied field here. This experiment is, I think, is in 5th sem or 6th sem. I will explain it. Using this magnetic field, you will have this experiment also. Using this magnetic field, you will control the using this electromagnets. By controlling the current connected to the electromagnets, you can control this magnitude of the magnetic field, and you can measure this magnetic field using Gauss method. So by experiment, you can determine your BZ value, and you can also determine your IX. See, you can measure, you can put an ammeter here. Once you put an ammeter here, you can record the amount of current Ix passing through this semiconductor. And also you can determine your hole voltage. How do you determine the hole voltage? You can just put a voltmeter probe here on the front side, and on the back side also you put another voltmeter probe. So if you connect a voltmeter like this, you can determine how much voltage is developed across this semiconductor. How much voltage is developed across this semiconductor. You can determine that. So these things are experimentally measurable. And also you can measure the thickness of your semiconductor using a screw gauge. This is the thickness of semiconductor you can measure using a screw gauge. So from experiment, you can measure all these things. Once you measure all these things, you will get the value of your Hall coefficient. Once you know the Hall coefficient value, if your Hall coefficient is minus, then you know that your semiconductor is N-type. If your Hall coefficient is plus, then you know that your semiconductor is P-type. All right. Now, you can also determine the concentration of charge carrier. If it is a p-type, once you know your Rs value, you know the electronic charge, this a constant, and P is the concentration of charge carrier, concentration of how many majority holes, how many majority charge carriers, that is holes, is available in the p-type semiconductor you can determine. And similarly from here, once you determine this, you know this value of a charge particle, 1 unit of charge, that is 1.9 per minus 19 coulomb. So you can also determine how many free electrons are available in this n-type semiconductor. That is the majority charge carriers value you can determine. All right. Now we also define that for n-type, the conductivity is given by this. Right. And so therefore mobility is this. And once you calculate the conductivity also, you measure the Hall coefficient, then you get your mobility. Right. And for p-type also, you can do this, you can calculate the mobility. So the advantage here is that, like, by performing this Hall effect experiment, you are able to determine the type of semiconductor, and also you are able to determine the charge carriers, and